Welcome. In this session, we'll learn the concept of time constant in RC network, but using simulations. All right, let's start. Now, before we use the simulation, now you can use different softwares to do the simulation of this RC circuit, but the one that we're going to use in this session is MATLAB. Okay, we'll use MATLAB to do the simulation of this RC circuits. But before we do that, let's revisit the this time constant concept. We know if we have an RC circuit, and if we connected this circuit to a source, okay, let me redraw this like this. This is Vs, and if we connected this source at t equal to 0, the capacitor voltage behaves like this. So the capacitor voltage is Vc of t, and we are assuming it's initially relaxed, or the capacitor voltage is initially 0. It behaves like this: t by tau, y tau is RC. All right. So we learned how the capacitor voltage changes in the previous sessions. So it behaves like this. If this is the final value of this, that's equal to Vs here, and the capacitor voltage rises like this exponentially. And we saw in 5 time constants, the capacitor reaches to almost to the 99% of the final value, 99.33 approximately, right? Or we say in 5 time constant, the capacitor reaches to the final value. All right. So based on what is the value of R and C, we'll see how fast, how much will be this 5 time constant. Now for the first example, let's suppose R is equal to 1, C is equal to 1. So what will be the time constant here? So time constant is RC, that's equal to 1. So the value of this time constant is 1 second. So in 5 seconds for this circuit, it should reach to the final value. Now final value is decided by Vs. What's Vs? If Vs is 1, then it should reach to voltage value 1, means Vc should be equal to approximately equal to 1 in 5 seconds. If Vs is equal to 10, then Vc should be equal to 10, approximately 10 in 5 seconds. All right, that's the meaning of this. All right, that's the first that we are going to observe from this. All right, so based on the value of this time constant, that will decide how much time it takes to reach to the final value, and how much time it takes to this reach to the final value. We're saying that's approximately equal to 5 time constant. And for this example, when R is 1, C is 1, it should reach to the final value in 5 seconds. All right. Now, if I say R is equal to, let's suppose for simplicity, R is 1, C is equal to 1 by 2. What's the time constant here? Time constant is RC, that's equal to 1 by 2, means in 0. So the time constant is equal to 0.5 seconds. So how much time it should reach, should take to reach to the final value? So if Vs is 1 volt, so if the value of the input voltage is 1 volt, Vc should be equal to 1 approximately in how much? 5 time constant. 5 multiplied tau is how much? 0.5. So in 2.5 seconds, it should reach to the final value. Or if Vs is 10, then Vc should be equal to 10 approximately in 5 time constant. 5 time constant means 5 tau, that's equal to 2.5 seconds here. For this example, when R is 1, C is 1. All right, and you can change this R and C and see the behavior. Right. The important thing that you have to keep track of is how much is 5 tau, because we are assuming that in 5 time constants, the capacitor voltage reaches to the final value, approximately reaches to the final value. That's the first observation. Second thing is, we talked about the behavior of this capacitor voltage. What about the capacitor current that flows here? What is the behavior of this capacitor current? So if we know the capacitor voltage, we can determine the capacitor current. How? By this expression. We know I is related to V by this expression in a capacitor. So we can say I of t will be equal to C dVc by dt. Right? So if we differentiate this expression, Vc is equal to this expression. So if we differentiate, it will be Vs into, what is the differentiation of this, is 0, minus what is the differentiation of this, e to the power of minus t by tau time is minus 1 by tau. Okay, so this is CVS divided by tau e to the power of minus t by tau. So that's equal to C, what's Vs, sorry, what is Rs? It is RC, C and C cancels. So it will be Vs by R e to the power of minus t by tau. So this is the current that flows. Now at t equal to 0, can you tell me the value? At t equal to 0, the value of this capacitor current or the current that flows in the circuit is Vs by R. Have a look at this circuit. What is happening when you connect the switch to the circuit? Have a look at this. Please pay attention. This is very, very important concept. When you connect the switch to the circuit seems to have only one element there, that's R, because there is voltage, there is resistance, and there is a current flow. There is no behavior of this capacitor. In other words, capacitor behaves initially as a short circuit. When you connect this supply to this RC circuit, capacitor base C behaves as a short circuit. So C is acting as a short circuit. All right. So this is very, very important observation from this expression. All right. So initially, when you connect the source to this RC circuit, capacitor behaves as a short circuit. Then the capacitor voltage rises, and that is given by this expression, and the current is given by this expression. Have a look at this expression, this current expression. Is it decreasing or increasing? It is decreasing. As time increases, it is decreasing. All right. And we shall observe these things from the simulation of this. Okay. Let's go to MATLAB and see the simulation. All right. So this is MATLAB. I know you guys don't know anything about MATLAB, so don't worry about it. Just pay attention to the components that I'm going to use. Let me use Simulink. Don't worry about this, what I'm doing here. What are the different components? Don't pay any attention to these because you don't know anything about MATLAB. Just pay attention to the components that I'm going to use. This is our electrical ground, means we are going to reference everything with respect to this. Okay, let me use a capacitor. So this is our capacitor. And then I'm going to use a resistor. I hope this is visible to you. I haven't shown shared the window yet. Sorry. I'm doing the recording using Zoom, please. Okay, this is our resistor and this is our capacitor. This is our resistor. So we are going to simulate this circuit using, and we are going to connect a source to this. So we are going to use a voltage source. So this is our voltage source. Where we are going to connect this. So this is our circuit. All right. So this will give us the behavior. Now this is used for reference purpose here. This is just a solver. Why am I using it here? Don't worry about this. Just pay attention to this. The voltage value, I'm going to set it equal to 1. Means I'm going to assume that the source is a DC source and the value of this voltage is 1. And have a look at what is the value of the this resistance. Have a look. I'm going to change the value of the resistance equal to 1 ohm. Okay, apply. All right, this might. So the value of the resistance is 1. Same way, the value of the capacitance is, you can set that here, and it's, I'm going to take it 1. Okay, this is the value of this capacitance. So what's the time constant here? The time constant is simply equal to 1, right? Okay, now I'm going to use components that you don't need to worry about. I'm going to use a voltage sensor to measure the input voltage. So this is our input. And I'm going to use a voltage sensor to measure the output voltage because our output is across this. All right, so this is the voltage across the. So here, this one is used to display the output here. So don't worry about these components. What are these different components? You don't know anything about these. Oops. What are these different components? Don't pay any attention. So this is our output. This is our input, and our voltage is 1, our resistance is 1, and capacitance is 1. So this will give us a time constant of 1 second. All right, so let me mark these signals so that, so this is the VC signal, means the output voltage, the capacitor voltage. This is the input. Input is a battery, and let me simulate it. Let me show you the screen. This is how the output will appear on this, and let me show you the value. This signal is also. Have a look at this. My input is represented by this blue curve. Okay, you can see the value is 1 and it is turned on at equal to 0. Now VC is this yellow curve. Have a look at this. What's the value of time constant here? 1. So approximately in 5 time constant, it should reach to the 1, and 5 time constant here is equal to 5 seconds. Have a look at this. At t equal to 5 seconds, the capacitor voltage is almost equal to the final value. All right, so this is the concept of time constant. So in 5 seconds approximately, the voltage rises to the final value. All right, now let me go back and change the value of the capacitance. Let me go back and change the value of this capacitance. Let me make it equal to 0.5. All right, so this is 0.5. And let me show you. So what's the time constant here? The time constant of this will be equal to, means what's tau equal? Tau is equal to 0.5 seconds. That means in 5 tau, it will should reach to the final value. How much is 5 tau here? That's equal to 2.5 seconds. Let me show you. After you run this, you will see it now reaches only in 2.5 seconds. Have a look. It is approximately equal to 1 in 2.5 seconds here. Have a look at this point. All right. At 2.5, the voltage of the capacitor is almost equal to 1. All right. Now let me go back and change the value of the input. All right. Let me change it. Let me first change the value of the capacitance back to 1 and change the input to 10 volts. Okay. Change the input to 10. And let me show you the plot. The plot looks like this. Have a look. In 5 time constants, again, the circuit voltage rises to equal to 10 volts. You can see in 5 seconds, the circuit voltage almost rises to this. So as you change the value of R and C, the time constant will change. And depending on that, that will show you how much time it takes to reach to the final value. All right. Now, again, let me go back to this and change the value of the capacitance to 0.5 seconds. Sorry, 0.5 farads. And once you do that, let me go back. So now it should reach to 10 volts in 2.5 seconds. Let me show you that. Have a look. In 2.5 seconds, it reaches almost to 10 volts. All right. So this is the concept of time constant in RC circuit. I hope you have got the idea from this. Now let's simulate the capacitor current also, or the current that flows there. Okay, let me go back. For this, I'm going to use the element that is current sensor. That will measure the current. All right. So this is the current, and three. This is the capacitor current, and let me show you the plot also. So first, let me change the value of this capacitance back to 1, and let me go back. So have a look at this. R is 1, C is 1. So in 5 time constant, the capacitor voltage that is given represented by yellow curve reaches to 10 volts. And have a look at simultaneously at the capacitor current. When the capacitor reaches to the final value, the capacitor current almost drops to 0. Have a look, because this is very intuitive. as the capacitor reaches to the final value of the this voltage, means battery voltage, the capacitor current must drop to 0. This is quite intuitive. I hope you have got the idea. So the capacitor current decreases as capacitor voltage rises. So finally, the capacitor should stop this flow of current. As the capacitor voltage rises to the final value, the capacitor current should be equal to 0. All right. I hope you have got the idea. All right. This is the concept of time constant in RC circuits. In the next session, what we'll do, we'll learn the concept of this time constant in RL network using simulation. All right. Let me end this session here.